the models are available. So I will first explain the problem. We have a CAD model of a part which is composed of small features and which has very arbitrary shapes. And then given this part, we have also user tolerances. So the user states that for each feature point or for each measurement point on the object, you have kind of a tolerance which is permitted to pass basically. So the company could live actually with these errors, but not less. So it provides certain specifications, and given that and the part itself, obviously, we generate a coordinate measurement report. So that report actually is basically a coordinate. For each measurement point, you have a coordinate in the coordinate system which they require. So we are not measuring distances or radiuses or anything, but the coordinates themselves. So there are a lot of challenges to this. First, it has to be online. It has to be installed on the production lines. It has to be highly accurate. The parts are around 2 meters, and we want around 0.25 millimeters accuracy, which is quite tough for such objects, because the metal parts themselves are composed of a lot of scratches here and there, and the fitting algorithms or anything which they don't work properly. So exactly, the system has to be static. There is no dynamic component on this system. So we will be installing a lot of cameras, and nothing will move, and the entire part will be measured at once. It should be easy to operate. So there is no operator who is standing by the machine and doing this. And we don't want any assumptions on the geometric types that we actually measure. So we don't want any primitives, or we don't want CAD specific algorithms. And obviously that has to be invariant into the geometric structure, so that you could measure any kind of geometry. So our camera arrangement in the virtual setup is shown on this left, and we use 45 cameras, which are twice the VGA resolution at a frame rate of 30 frames per second. And we use lenses about 25 to 50 millimeters. So this is like the arrangement we do in the real setup. And we use a lot of white LEDs to illuminate properly. And so the network is actually shown on the right. And here you see that we have camera groups. And all these camera groups are specifically designed to inspect one feature point, one measurement point. So these are local camera groups, and there are no overlaps between those. And the images that you see on the bottom are coming from random cameras, and these are the holes and geometric structures to be measured by the system. So we have to calibrate this. And of course, the intrinsics are easy. You just take all 45 cameras and calibrate one by one. But the extrinsics become a problem because there are no overlaps between the cameras, and the overlap only lies within the local camera groups. Then we kind of manufacture a calibrator object, which is not manufactured precisely, but we augment this calibrator, this rough approximation of the actual part that we inspect, with a lot of circular markers, circular points. And we take an external system and actually triangulate this 3D, actually reconstruct these 3D feature points, 3D circles. And then for each camera, we do an extrinsic pose estimation, which gets the camera location in the global coordinate frame. And then the measurement, basically the measurement is a projective LM-ICP. This is a variant of ICP. Iterative closest point, but not in 3D space, but at each iteration you basically project the CAD model onto the image frame and then minimize the distances there. And this is like kind of the equation which lies. So this is the steps, and you basically fit the CAD models to the images and then get the position. And we do an extensive evaluation on this, and our accuracy is basically, we prove that the precision and accuracy are sufficient for these industrial applications. And I omit a lot of details, and see you at poster B5. Thank you for your attention.